What's the first step?
Move 7.
I love it. Make some room, because the process you want to use to complete a square needs some room. So put some stuff in there. So you make a little room. So well, how do I figure out what's going to go there, and how do I figure out what's going to go here? Yeah, so the first step is take negative 10 divided by 2. So that's going to go where?
On the X part.
It's going to be how it factors. I don't know if you realize how freaking nice that is. That's why no matter how ugly the number is, I put a very nice number in there right now, just so we can all remember how this works. No matter how ugly the number is, the process doesn't care. It's awesome. You don't have to factor anything. It already tells you how to factor. And then how do I figure out what goes there on both sides?
25.
Yeah, square that bad boy. 25. So I add 25 to both sides. Oops, got it. Yeah.
If I have minus 25, I should put minus negative, outside? Or,
Yeah, and the only way you would really have that, if you think about it, is if this itself is complex. Because the squared step, if it's real, it's always going to come out positive. Right?
Yeah.
Cool. If for some reason you have a complex number, an imaginary number here,
Yes.
then it might be negative. Then you just subtract from both sides. You put a negative 25 on both sides. Yeah. And again, if you're just coming in, there's the Chapter 9 homework for the Blue Book. All right, and where do I go from here? Square root both sides. I like it. Because I can't do a damn thing with, I'm trying to get x by itself, but x is stuck inside the square. So I directly kill it. The minute I do that, or the second I do that, what do I also put down? Plus minus. All right. Well, that's be just second nature. It just shouldn't feel right to do a square root on both sides without putting that plus or minus. So I kill that square there. What can I do with this?
3 by 6.
I love it. 18 can be broken up as 9 and 2. Square root of 9 is 3. Square root of 2, I don't know.
Add 5.
Yeah, and then add 5 and you're done. X equals 5, give or take 3 radical 2. So now to check it with the quadratic formula, you have to know what the quadratic formula is. And we all know that. And now once you know what the quadratic formula is, you have to know what it needs from us, what we have to feed it. All right, quadratic formula is this little beast. I want to feed it what it wants. What does it want to be fed? ABC. And what's ABC? And in this case, A is 1, negative 10, 7. Cool. And then you just throw that stuff in there. Right? And somehow it's going to come out to be this. So go ahead and take a second if you haven't done that already.
So in order for you to do a quadratic formula, it has to be a squared, right? It has to be squared there? Or no?
Yeah, it's got to be the form ax squared plus bx plus c. Yeah.
Can you go any farther with that answer that's circled?
Not really, because there's no like terms.
Okay.
The radical's been simplified.
Maybe 5 plus 3.
Yeah, I could write it separately. 5 plus 3 root 2, 5 minus 3 root 2.
Yeah, that's what I thought.
There's the two answers, but
Yeah.
it's fine to go ahead and write it like that.
Okay.
It's like saying x not equal to plus or minus 4.
If you wanted it, somebody wanted part to be like 8 or 2.
No, careful. You can't add the 5 and the 3.
Oh, you can't?
Because that's 5 plus or minus 3 times
Right.
radical 2. You can only add anything if they were like terms.
Oh, that's right. If you took it out from under the radical, then you could put it right.
If this had a radical 2 on it, or if this didn't, then they could be put together.
Yeah.
Yeah. So doing this here, negative b, so negative negative is positive 10. B squared is 100. Minus 4 times AC over twice A. What do you get underneath the radical there?
72.
Yeah, 72. And of course you can simplify that.
6 to 22.
Good. 72 is 36 times 2. You always try to break it up into the biggest square you can. 9 goes in. That's 9 times 8. 8 still has a 4 in it. That's 36. That's square rootable. So if I make that into 36 times 2, I'll get 6 rad 2 over 2. Is that cool? Rad 36 is 6. Rad 2, I don't know.
2 on 6.
And then everything can be divided by 2, so I'm allowed to do that. I can't divide one or the other one. I have to divide both. So it becomes 5 plus or minus 3 rad 2. Thank God it's the same thing we have there. And of course it is, because that's just a shortcut to this. Okay, cool. Okay. Can I turn this thing off? Yeah. It'll drive it crazy. Okay. All right, so let's try one that's a little uglier than any that we've done yet. Yes?
Question.
Yeah.
What's the purpose of complete the square?
Right now, I wouldn't blame any of you guys, and I think I said something about this the other day, but I wouldn't blame any of you. Go, why the hell would I ever do this show? I'll just always do that. Because this is not the only place completing the square does something. Very quickly, what's important about that? Yeah, if I put a line in that form, I know the slope, I know the y-intercept, right? So later, well, not really later, not really at all in this class, but if I could put this formula in this form, I could see the vertex HK. So it's sort of like y equals mx plus b. If I complete the square and put it in this form, then I can see the vertex just sitting there looking at me. Just like if I solve for y, I can see the slope and the y-intercept, right? And then later, you would talk about, and we will talk about this in the last chapter, in the conic sections chapter, if you've looked ahead on your formula sheet. This is the equation of a circle with radius 5. Kind of nifty. This is the equation of a circle with radius 5 that has a center at AB. How do I get it in this form? Complete the square. Right? So completing the square, one of its most important duties is to put certain types of functions in the right form. Just like solving for y is the right forms for me to see things, completing the square is the right form for me to see things with these squared equations. Is that cool? This is a good question. That's always a good question. Why in the hell would that be necessary besides to fill up time in your math class, Jeff? There are reasons for it to exist. And where did this come from? Using completed square on ax squared plus bx plus c. We couldn't even officially use the quadratic formula unless we knew this. Then we could prove that, and now we're allowed to use it. Cool. Okay. So, what about a more disgusting example? Let me go ahead and put it here. And to make something more disgusting, do that. This is disgusting for two reasons. First, the middle number 7, which is not something I can cut in half as easy as I'd like to. Secondly, it's not in the right form for completing the square to work. Now, I said this yesterday, but it was sort of in there real quick. Somebody know what's kind of there that shouldn't be there? Well, I made it even worse than I wanted to, but oh well. This can be a fun one. Second? The 2. Completing the square is built off of the first number being a 1. That's what it's built off of. So it doesn't have to worry about that number. It would be a much more disgusting process if I try to build it in, the first number being anything. So I have to first, in this case I could just divide by 2. Is that cool? Yeah, so divide by 2. I get x squared. And now I just start attacking this thing. What do I have to do first? Yeah, get the 1/2 out of the way. Make some room.
Did you do that one with the quadratic formula too?
Oh, hell yeah. Quadratic will eat up. It will just eat up any quadratic equation that I have. If I can identify those coefficients, the coefficients could even be complex. It could be, I don't care. And there's actually more that you could do with that quadratic equation than you currently realize. Mainly because I haven't told you yet. But I could do stuff with higher powers here, as long as the middle one is half that first one. See how that's the first power? That's the second power. So if I had an 8th power here and a 4th power there, I could use quadratic formula on that. You should expect it to be a little more complicated at some point, and it is. But I could use straight up quadratic. But let's see how far you can get. Try to do this. Remembering that the process doesn't care that there's an ugly fraction looking at you. I know you care, but see how far you can make it. Lucas? You out there? There.
Arturo?
Just remember, divided by 2 is the same as multiplied by 1/2. That might help out a little bit on the very first step.
You can graph those. You can graph those.
Can we graph those?
Yeah, the question.
Oh, are we going to?
No, we graph it or not.
You can have the graph?
Mm-hmm.
How do you,
Like, I don't know, just the answer, so you graph it or just that's it.
no, just that's it. You don't have to graph it. Yeah. On the graph, those would be the X-Intercepts, right?
Mm-hmm.
If you did graph the parabola, that would be where it hits the X-axis. All right, let me try to catch up to you guys. What's my first step? Yeah. So first step, I take -7/2 and I cut it in half. So I get -7/4. And what's good about that?
X minus 7 squared.
So in here, what's going to go there?
X minus.
Yeah, x minus 7/4. That kicks ass. Don't forget. I don't care what that number looks like. The first step tells you what's going to go in the factored form. That's beautiful. And the second step tells you what's going to go there and there to make that happen.
49.
So second step, take that thing that we just got, square it. You get
49.
49 over
16.
16. So I have to add that to both sides. Yep, so then add these, you have to give this LCD. So it'd be 8/16, right? Negative?
41 over 16.
Yeah, good. So 49 minus 8, 41 over 16. We should be at the point where we're annoyed when there's fractions in a problem, but we're not freaked out. I mean, we shouldn't be, we should be like, oh shit, we should be like, oh shit. All right. There's a difference between those oh shits. Here, of course, square root it to to kill that square?
It's minus.
Plus minus. So here, I'm just left with the inside. The square went away. There, what could I do the square root of?
Square root 41 over 4.
I love it. Square root of 16 is 4, so I could just put a 4 down there. Square root of 41, I have no idea. And then add the 7/4 over, right? So, I mean, really look at that and think that wasn't that much more difficult than the one where I had a 10 in the middle, right? The one where I have a 7/2 in the middle is really not that much more difficult than when I had a 10 in the middle. And 10 is a much nicer number to work with, right? Okay, hopefully you guys agree. Then you get x equal, add that 7/4 over. 7/4 plus or minus root 41 over 4. Of course, you could tell that from the beginning. No. All right. Yes, sir.
And then you can just write the whole thing over 4, right?
Yeah, sure. Yeah, exactly. You're like reading my mind. In my brain, I'm thinking, okay, if you put it all over that, that looks more like what you would get from quadratic formula, because quadratic formula puts it all over that bottom. Cool. Okay. Now here's the thing we did last time, and I want to show you all the way through how it could be used. And the main thing we talked about last time was trying to explain how to find the most important point on a vertex, on a parabola, which is the vertex. Ooh, that's kind of mean. Oh, well. Make this 9 I'll make something we can graph easy. Make that a 12. Yeah. So I have a fraction show up at the moment, because now I'm going to show you something new, how to kind of go to graphing this straight from what we can find here. What's the quickest way to find the vertex? I love it. So define the vertex. And if you weren't here last time, the short version of this, there's the quadratic formula rewritten a little bit, kind of broken up, right? Notice that, oops, got a plus or minus, that is in the middle of the 2 intercepts. So when you do the quadratic formula, you actually find the X-Intercepts, because you're finding where that thing equals 0. The vertex would be right in the middle of those 2 intercepts. Is this, give or take this? So what's right in the middle of those 2? That dude, right? So we had a little discussion last time. So right in the middle would be negative b over 2a. I add something to get to one intercept. I subtract that same thing to get to another intercept. So that's got to be where the vertex is. So that's why it's a nice shortcut to find the vertex. I do x over equals negative b over 2a. And then y is going to be, plug that thing back in to the function to see what the y output is. So when I do negative b over 2a, I find out where the vertex is. And when I plug it into the function, I find out what the value is there. So in this case, what do you get for, yeah, what's b? 12. A is 3. So I get negative 2 for the x. So I know my vertex so far is negative 2, comma something. And to find that something, I just have to plug in negative 2. So you get 3 times 4 is 12, minus 24 is negative 12, minus 2 is negative 14. How are we doing so far? Is that all right? So now my vertex is at negative 2, negative 14. Can anybody tell me real quick what the y-intercept is? Should not need much work at all.
Minus 2.
-2. 0, -2. Right? Because when you plug a 0 in for x, you get that number there. Sort of like mx plus b with more crap in it, but same reasoning. All the x stuff disappears. So my y-intercept here is 0, -2. So now I can graph this thing.
Excuse me.
Yeah.
So you get -0, -2 from the first line?
Yes. Because when I plug a 0 in for x, I'll have the y-intercept come out. And when I plug a 0 in for x, I get -2.
Okay.
That's one of the most easily forgotten things, by the way. If you want to find any intercept, you make all the other letters 0. We normally only have 2 letters to worry about, but didn't we earlier this semester have like x plus y plus z equals 7? So how do you find the Z intercept? You make x and y 0. Boom, right? So I had an equation with basically every letter in the alphabet in it. If I want the W intercept, I make all the other letters 0. It's kind of silly. Never forget that. It's always that simple to find an intercept. So to graph this thing, in a way, hopefully somebody feels like we don't have enough information. You should really have 3 points for something that turns. And we do, actually, believe it or not. Then we have the most important point, which is the vertex, right? Let's see, let's go by 2, 4, 6, 8, 10, 12, 14. So the vertex is -2, -14. Then we have one other point, it seems. We have the y-intercept is 0, -2. But we actually have one more point. Because what is true about a parabola? If I know there's a point here, there's got to also be a point straight across from it there. You with me? So we know it's got symmetry to it. So let's use that so I have to do less work. So if I know there's a point here, which is 2 away from this thing here, from where the vertex is, are you guys with me? If I drew a parabola for you and I said, draw me where the mirror is, to represent the symmetry, where would you put it? Right down the middle. So this is called the axis of symmetry. That's something else. Right. So if I know that there's a point 2 away here, there's got to also be a point 2 away on the other side. Now those 3 points are plenty to make the parabola. It kind of gives me the shape, gives me the groundwork for this pretty skinny little parabola. Yes, ma'am.
Question. So, at first you put x equals -b2a, and then it turned into a world of y. Why is it a y if it was an x?
No. Here's the x work. X equals -b over 2a. So I picked up the b and the a and then got that. How do I find the y value? Well, if I have x, I just plug it back in to get the y. So here's the work for the x piece. Here's the x piece. Once I have the x for a function, how do I find the y? The y is just the output. So I just plug it in. If I plug that x in and see what comes out, that's the y value.
And how did you get that one up there? That's just from the problem at first?
Yeah, y-intercept. At any point I can find the y-intercept, but here's the function. How do I find the y-intercept? I make x 0. So if I make x 0, those go to 0. I'm left with -2. So that's why I said it's a lot like the mx plus b. Whatever number is sitting out there actually ends up just being the y-intercept. It's the only thing that would be left alive if you made all the x stuff 0. So here's my axis of symmetry. A little bonus question. Can anybody tell me the equation for the axis of symmetry for this parabolic function? What's the equation for this axis of symmetry? It's a vertical line. Do it again. I like the attempt, but no. Yes, there you go. See? Yeah, 50-50. So the axis of symmetry's equation is x equals -2. So for any parabola opening up or down, the equation of the axis of symmetry will be x equals something. In fact, x equals the x piece of the vertex, right? the axis, the symmetry's got to go right through the vertex. So if I know the vertex, if I knew the vertex for something was 7, -3, what's the axis of symmetry equation? X equals 7. It goes right through the vertex. Now there are parabolas that open left and right. Let's not worry about those at the moment. We're going to stick with up and down. How you guys feeling so far? Is that decent?
So you just did basically the opposite to get the other end of the parabola? I don't understand.
Yeah, it's symmetric. It's like the mirror image. I did the mirror image point. So here's the mirror. There's a point that I know it's the y-intercept. What's the mirror image? It's going to be 2 back this way. So here I am looking at my mirror. There's a little dude looking back at me. The same distance on the other side, right? So it's just that mirror image point.
Will you always do that?
Yeah, I would. Yeah. So if you know the vertex and one other point, you're good to go because you got the reflection point too. And that's all you need to make that curve.
How do we know to go to the right or the left when we're here?
Because it's around the symmetry. It's around the middle, right? I wouldn't go this way because my mirror is here. Yeah. That would freak me out if I look in the mirror and my reflection's standing behind it. It'd freak me out a little bit. Yeah.
I don't know, always touch the axis.
Do it again.
How do you know? Here we know from y-intercept is 0 minus 2. So touch the line for the y-intercept, the y.
No. Okay. So it's coincidence that this number is the same. I could have put anything there. Would that have affected the vertex at all? No.
No, maybe when you graph, but doesn't touch the x or y. How do you know?
Oh, if I had a point here,
Yeah.
then you just go the same distance away on the other side. That's all. So any point you know, if I know a point here, I see how far away it is there, I go the same distance there, and there's another point on the graph, because the symmetry around the mirror, around the axis. So the y-intercept is normally the easiest one to get. If for some reason I can't get, I got something else, then I use whatever other point I got. I just go the same distance on the other side to find its reflection. Cool.
How would you tell that the parabola never hits the x-axis? If it's like on top of it?
Well, if it opened up and the vertex was up here,
Yeah.
that would do it. So if I had a vertex here and it opened up, it's never going to hit the x-axis.
Right.
Yeah, that's
Right.
what
Would it
mine
look
is.
would it look any different like in the equation and the f of x stuff?
Now think about this, it's kind of cool. The way that equation is now, it goes down to -14. With me? How can I pick this whole thing up, do you think? How can I move this whole thing up? I take this equation. Alright, we're getting into neat territory now. This equation. How far would I have to move it up so I get it up here? At least 14, right? So maybe 15. Well, if I just add 15 to it, so then I get 3x squared plus 12x plus 13. That thing would have no x-intercepts.
Oh, I see.
It would be up here. The vertex would be above there, and it would go up from there. It wouldn't have any x-intercepts.
Oh, I see.
Once you graph something, you can kind of see, well, what do I have to do to make it go somewhere else? I have to lift this whole thing up. So I lift the whole thing up by doing that. Can you just do that if you want to? Of course not. I'm just showing you if you had that power, if you were the math god, and you said this function shall change. You have to add 15 to it to make it go up there. What would that mean about the quadratic formula? If you apply the quadratic formula here, what kind of numbers would you get? Real numbers. That's the important thing. If you applied it here, you would get complex numbers, of course, right? Because when you do the quadratic formula, what are you actually getting? What are the answers going to be? In fact, do it. Do the quadratic formula on that function there. I'm not getting the feedback I want, so I'm going to make you work. So apply the quadratic function here, and then I want somebody to tell me what the hell you just got.
Because we need just use this formula without solve.
Oh yeah, we'll figure it out. Plug stuff in, figure it out.
I know.
Just plugging stuff in. One of the most common mistakes is people forget that one of these is negative, so you should end up adding in there. Sometimes you get complex answers when you shouldn't. Here you just get the wrong answer. But so it should be 144 plus 24. So 168. So 4 will go into 168. You can simplify this a little bit. Not a bunch, but a little bit. 4 goes in there 42 times. Cool. And 42 is 6 times 7. I can't do the square root of either of those, so it's not going to go anywhere. So that's as simplified as I can make it. So if I take this and make it, if I do this 4 times 42, the square root of 4 is 2, and the 42 has to stay inside. And then I can reduce it a little bit, right? It's always your last step on these kind of problems is see if you can reduce it a bit. Tell you honestly, I'm going to go a little further than that. So I can divide everything by 2. Is that cool? And of course, you can even go a little further. You can split that up and make the negative 6 over 3 is negative 2. And then radical 42 over 3. Whatever the hell that is. What part of that jumps out as making supreme sense as far as what we've already done?
How do you graph that?
Do it again.
How do you graph that?
Figure out what it is, decimal-wise. Get an approximation, right? I don't know what the hell it is, but get an approximation for it, and then you can graph it.
How do you from the negative 12 over 6 to negative 6 over 3?
So I took a 2 out of everything.
Yeah, but
Canceled it.
we still have to. I still have to do it.
Say again?
12 divided by 2.
The 6.
Yeah.
2 divided by 2 is
Oh.
gone. 6 divided by 2 is 3. Yeah. So just divide everything by 2. The only way to legally reduce something like this is if it goes into everything, right? You can't just do this unless you break it apart. So I went and broke it apart at the end here. You guys see, what's the vertex again for this problem?
Minus 2.
Negative 2, negative 14, there's negative 2, right? The negative 2, give or take this much. So it shows you that this is right in the middle of the 2 intercepts. And note, one intercept should be just barely above 0. So what's negative 2 plus square root of 42 over 3? Somebody help me out. I'm looking at the 2 intercepts I just got. Negative 2 plus radical 42 over 3. Sorry? It's a little too much, I think.
0.16.
That sounds better. Oh, yeah, subtract 2 from it, right? Did you do negative 2 plus? Yeah, so 0.16. That makes sense from that picture, right? Even though my pictures very often suck, I at least know if it's going through the y-axis there, it's got to be a little bit on the positive side there. So that x-intercept makes sense. And the other x-intercept from my horrible scale looks like it should be around 4, negative 4, right? I bet you it's actually going to be negative 4.16, something like that. So if you do negative 2 minus radical 42 over 3, you will get negative 4.16, I'm hoping. So it's about right, my picture. My scale sucks a little bit, but it's close. Do you guys see all those pieces? So you know how to find the vertex. You know how to find the x-intercepts. You can just do the quadratic formula if it doesn't factor. And that thing sure as all hell didn't factor. And then the y-intercept is easy as hell always. Just make x 0. Yeah.
So which one we use?
How do you mean which one to use?
We use this. One of we.
If I ask
Or this
for the vertex and all the intercepts,
We use this.
then you have to use this also. This is how we got the X-intercepts, right? Ay, ay, ay. All right. Okay.
Excuse me.
Yeah.
Ask about -2. From where?
-6/3.
Okay. The 3 is it should go on.
No, because you got to divide both of these by 3.
أنا حماجتها.
This and this are divided by 3, right? So I can break them up, but I'm not allowed to make that one disappear. Yeah. Okay. So I'm hoping that what you take away from this is that I will definitely give you a problem where I'll give you the function. I'll say find the vertex, all the intercepts, and then graph. You will definitely get that problem from me, right? And there are several in the homework exactly like that. So you have some practice, right? Is quadratic formula difficult? It could be annoying, but it's not difficult, right? Is the negative b over 2a stuff difficult? No. Is the y-intercept difficult? Hell no. And then all you have to do is plot what you got. Right? If you get ugly ass x-intercepts, don't even worry about it. You got the y-intercept, you got the vertex, and you got its reflection, and you just kind of make sure it looks like it's heading in the right direction for what you get for the x-intercepts. Right? I'm not going to try to plot 0.16. Mine are definitely not that nice to be able to find that on my graph. Yeah.
Why you use this? I'm sorry, like I don't understand.
I like it. So, what does the quadratic formula do?
Yeah.
Check.
What does it do? I don't know, man. We throw stuff in and it gives me stuff out, Jeff. What more do I need to know than that? That's what math is.
Finds the X-intercept.
Finds the x-intercepts, right? I mean, how do you find the x-intercepts? You make y 0. So if I made y 0, that's effectively setting this equal to 0. How do I solve that? I try to factor it. If I can't factor it, I use a quadratic equation. Quadratic formula. So what does the quadratic formula do, really? It solves the equation this equals 0, which finds the x-intercepts. Those are all equivalent statements. So if I ask you to find the x-intercepts for a quadratic equation that's not factorable, that's what we have this for.
For on the homework for 3.1, is that what we're supposed to do on number 10?
For which book?
The white one?
In which section?
13.1.
And which number?
Number 10.
Oh, number 10 just says how many real solutions are there. So if I give you a picture like this, how many real solutions are there?
This one.
One. That one right there. Right? How many real solutions would there be for this equation? There'd be one, because there's one x-intercept. How many real solutions are there here? 2. How many are there here? None. So here it would be all complex. Both the answers would be complex. b squared minus 4ac would be negative. I'd get a radical of a negative number. Here I'd have a repeated, like x minus 2, x minus 2. That's why it's one answer, but it's just repeated. And here's one like we just did, right? I get 2 real answers. Okay. So it's kind of nice that the work we do here exactly correlates with the pictures we see. Right? So what could I get here? What kind of answers could I get? I could get real answers, so it'd be like this. I could get complex answers, so it'd be like this. There's a visual that corresponds to every possible thing that could happen. Of course, I could get one answer where this becomes 0, and that would be this.
I have a quick question. So how would you solve that again? Negative 2 plus or minus root 42 or 3. How would you do that again?
Just put it in the calculator.
I don't know how to do that.
So do negative 2 plus this. So if you don't know where your square root button is or something, just ask me. I can show you.
It's right here, Rob.
I got. So then just put in negative 2 plus radical 42. If it opens a parenthesis, you better close it. Right? Just Depends on what version of a calculator you have. Some of them are like Microsoft Word. They assume I want a parenthesis. I hate that. So when you do -2 plus, if that opens a parenthesis, you better close it, and then you say divided by 3. Bam. And the other one, just put a minus in there. This is where the student asked me, where's the plus or minus button? But you just have to do both of them separate.
So 2 points for the X.
In this case, there's 2 X-intercepts. There don't have to be, but in this case there are. Yeah. Okay. So a little summary. So you know you can expect this type of problem from me. I'll give you a function. I'll ask you for the vertex, the y-intercept, and the x-intercepts. How do you find the vertex?
Minus b.
X equals -b over 2a, and y equals what you get when you plug it in. Y is the output for that input, right? How do you get the y-intercepts? Yeah, I love it. If it's in this form, the y-intercept is 0c. You set x to 0, and if it's in that form, you're going to get that. Kicks ass. And then how do I find the x-intercepts?
Minus b plus minus square root.
Okay, yeah. So either you factor or quadratic formula. Okay, cool. How's that? That's your recipe for that kind of problem. And then I'll ask you to graph it, and you just put all the points you found and connect them up.
This will be on the quiz tomorrow.
No, this won't.
This section is?
No, this is section 13.7.
Oh, okay.
Yeah, it's only going up to 13.2. I don't know if you ever noticed that. The semester's almost over, but if you haven't noticed, I never put something on a quiz that we just talked about the time before. I always give you at least 2 class periods in between. Just because I'm still nice. Right, give me a few more years, then I'll be mean. Okay, so now comes the part that I really like, because this is the immediate value of knowing the -b over 2a thing. As I promised somebody, I'm going to put this up here. That was exciting. All right. We had a great class. We sat there and watched them play with their damn screen all day. Whoa.
Which page?
Page 864 in the white book. Okay. Just don't do it. Can you guys see that? Nope. Okay. Could you grab one of the lights back there? If one says whiteboard or something, that'd be good. One of them doesn't do anything. Throw those back on. Oh. All right. Now, part of this should not sound different at all. I mean, this is, they've given you a little picture, obviously too much of a picture than you need. You know, little people there for you. But the most important part, of course, is just the shape of this. It's going to be some kind of rectangle, possibly square. I don't know. One side is against the house. So you see this kind of thing all the time. You see that where they're going to build a pen, and one side is by a river. And whatever you're going to put in there don't like to swim, so you don't have to fence that side off or whatever. Here, I don't have to fence this side off because it's right next to the house, right? And if I do have to leap over the fence to get out the back door, that would suck. So I just need a fence in around here. So what would you call? I wonder if I could do that. Actually, kind of cool. What would you call this here? X. I love it. What would you call this here?
Y.
Y. I love it. Sweet. All right. We're going now. So I got X by Y, because I don't know if it's square. I can't say X by X. I would be saying it's a square. I don't know if it's a square. So I've got X by Y. That'll work. So this is X. This is Y. And there's X, right? Now what do I know about this fencing that I'm going to use?
60.
Yeah, 60 feet of it, right?
60 feet.
So somebody give me that as an equation based off of what we got here. What would that equation be that governs that 60 feet? Don't go too far. It's not area.
2x.
Yes, I love that. I need 2 x's and a y to make 60 feet. I need to, my 60 feet is going to go into 2 x's and a y. Is that cool? Not too bad, right? So this kind of problem is called an optimization problem. This is I just want to start with something visual, but then you're going to have profit, and this is exactly what I was talking about before. You want to maximize your profit. Where are you going to get on that vertex of that profit function, right? Here I've got the same kind of thing, but I just want to know what's the maximum area I can get. In fact, real quick, real life observation. What shape are silos where they store grain and stuff? What shape are those normally in? Cylindrical. They have a circular base, right? Because as it turns out, the circle is the thing that gives you the maximum area for the same amount of material. So if they would have made that rectangular or square, they wouldn't have got as much area. And of course, when you're storing stuff, well, if you multiply the height and you got volume, you're worried about the volume so you can store more stuff and spend less money making the damn thing. So that's why silos naturally became circular, and the math said, oh, you're doing that right. Right? So yeah, that maximizes the volume. So there's and this kind of problem, for an optimization problem, they pretty much always tell me something, and then they ask me something. So they just told me straight up the perimeter is 60. So I can write an equation that I can use. Then they ask me about what? What do they ask me about physically? Area. And what's the formula for the area going to be?
X by Y.
Yeah, xy. Right? Just multiply the length times the width. Now, I can't do a damn thing with this. There's two variables in there. The area is just the area function. But the beautiful thing is I have this. How can I use that, what they told me that I know for sure, to help me with this?
You can use 1 and 2.
Yeah, I could use it's a system of equations. You don't have to look at it like that in case system of equations bug you. I just have too many freaking variables. Let me solve this one for y and plug it in. Alright, so take a minute and try that. Solve this guy for y. Plug in what you get there. Multiply it out and then step back and look at it. See what you get. Ooh. Yeah, I know. I'm just thinking they're like, oh, there's those math people looking at us again doing their stupid problem. course, when you solve this for y, you get 60 minus 2x. So you know y is that, so you replace y with 60 minus 2x. When you multiply that out, you get 60x minus 2x squared. That is quadratic, right? It's got a square in it. What kind of parabola would it be if I graphed it? Very strange question, but the main different types of parabolas are they go up or they open down. So this would open, careful, down. The x squared is negative. Right? Sort of out of order here, isn't it? So if you wanted to, you got to be careful about what a and b are. You can't just change them by going, let me do this. A is in front of the x squared. B is in front of the x. C in this case is 0 because there's no number. Are you with me? So be really careful about identifying things correctly. What's the quickest way to find? So this is going to be a downward parabola. I want to find the maximum area. So of course, where does that occur? At the vertex. And of course, what's the quickest way to find the vertex? Negative b over 2a. Right? So it's an immediate application of that negative b over 2a. Every single problem in this section, you start off with two equations, you use one and the other one, you end up with a squared thing. X squared somewhere. So you can find the negative b over 2a, get the vertex real quick. So what do you get when you do negative b over 2a? What's b? 60. And what's a? Negative 2. So you get 60 divided by 4, which is 15. And what the hell is that physically? What is that physically? Going back to our yard there, our fenced-in area, where we're going to put our kid. Let him roam. Yeah.
Why is 2x a and 60 b?
Because what's the main form? ax squared plus bx plus c.
Oh, okay.
So where's the a? In front of the x squared. So if you want to, you certainly could rewrite this as negative 2x squared. And then there's a and there's b. But just because somebody put it out of order doesn't change what a and b are, right? The vertex can't magically shift just because I moved my equation around. When I was a little kid, I actually thought that way because I was a major geek. I thought if I had equations, I could just move them around and the universe would change. And then I found out, no, that's not the way it works. So, too bad for me. So what is that physically? Has somebody told me that? Yeah. What is x? What does that mean? Yeah, it's the side of the thing. So this side has got to be 15 feet long, right? So how long has this side got to be?
30.
How do you get that? Yeah, you got y equals 60 minus 2x. If x is 15, 60 minus twice 15 is 30. So this side's got to be 30 feet. And what they actually asked me for, what's the maximum area that they can close? We got the dimensions now, right? We got the dimensions of this thing. It's 15 by 30. What's the area itself then? Just multiply those things together. Or, right here, you can just plug in 15 to see what the area is, right? But to get the area here, you just multiply 30 by 15 and you get 450. Neither. So I always try to teach that problem the same way. They will all pretty much always tell you something, the perimeter or whatever, then they'll ask you something. And you use what they tell you in what they ask you to make an equation to work with. Let's try one more of these. Let's try one that's not so visual. What was it? One number 7 there. That's funkadelic. So somebody sat down and was obviously very bored, and they plotted the rainfall in Sonoma, California, and they said, oh, this function here actually models that rainfall from January to December, right? So a very quick, strange question. Can anybody tell me what the domain of that function is? Now you're looking at the function, aren't you? But what's x?
2.
What's x in general? 1 for January, 2 for February, 3 for March. So what can it go from to? From 1 to 12, thank you. Right? So you don't try to plug 13 in there. That wouldn't make any sense, right? Unless we suddenly have a 13th month. You guys kind of with me? How important is that really? Well, sort of, but not really. My vertex better show up in between 1 and 12 or it don't make a damn bit of sense. Okay, maybe. But they give me the equation here. That's a lot easier than the one we just did. We had to come up with our own freaking equation. How do I find this guy's the least amount? Why is it the least? Why is there a minimum? Because this parabola would open... Which direction would that parabola open? Up. How do you know that? The x squared place is positive. But what happened to my x? Yeah. So, right? So it's going to open up. So there's going to have to be a minimum. Right? And thankfully, their domain is restricted because otherwise at some point they're going to have, if you can go infinitely high precipitation, that's kind of not good. Okay, so how do I find the vertex? They give me the equation, straight up.
Minus b over...
Yeah, to find the vertex. So it'll be negative b over 2a. What's b?
2.8.
Negative 2.8. And what's a? 0.2. Gross numbers, but we don't care. We have calculators. Right? Are you going to do that? No. What happened? You get number 2? I don't know. Okay. So you get half of what you just said. You get 7.
Yeah.
So what month do I get the least amount of rainfall? That's where my vertex is, right? My vertex is at 7. X represents the months.
July.
So the 7th month is July. Cool. I like it. Which makes sense. It pretty much is California. Summer... A trace is a lot. How much precipitation occurs in that month? How the hell are you going to figure that out? You know when that happens.
Plug it back in.
You plug it back in. That's the precipitation. That's why it's a P. That's the precipitation function. So if I plug in 7, I'll see how much actually falls then. Very small amount.
So everywhere there's a x, we put a 7?
Yes, exactly. It comes out to 0, right? Is that 0? 0, yeah. Okay. So they get no rainfall in July. Yeah. Just plug in a 7 in. So 0.2 times 7 squared minus 2.8 times 7 plus 9.8. Cool. Okay. So that's the word problem section, but they're nowhere near as horrible as a lot of the word problems are. They're going to set themselves up pretty easily, hopefully. Some of them are just going to give you the function directly. Kick ass. You just attack it with negative b over 2a. One of my favorite kind of problems, which normally means trouble for you guys, but is that one. We have a certain amount of metal, and you fold it up on both sides to make like a gutter or something, and you want to try to maximize your volume. I think I assigned that one. Fun with that one. All right. Oh. Okay. Can you turn the lights back up? Thank you. Maybe more? No? I could work in darkness. I do that. Okay. I think there's one more. Okay. So I just want to do, let's see, oh good. That's right. I want to get into chapter 14, which is chapter 9 in the Blue Book. We're eventually going to talk about exponential and logarithmic functions. And everybody makes a big deal out of logarithms, and they're not a big deal. But the first thing we have to talk about, I have to talk a little bit about inverse functions. This is something we haven't done yet. And the idea of an inverse function is really pretty straightforward. It should be the function that does the opposite of some function. So if I have a given function and I want to know what does the opposite. So if I had a function that was x plus 5, what would its inverse be? This is the symbol for inverse function. I love it. Not 1 over x plus 5. This does not mean reciprocate it. This just means the inverse. That's the symbol they chose. An unfortunate symbol, but oh well. That means the opposite function. Okay, cool. So if I put a 2 in there, I get a 7 out. If I get a 7 in there, I could get a 2 back out. It undoes it. You with me? Maybe. So if I put a 2 into here, what do I get? Come on now. Which one am I plugging it into? F. Not F inverse. So if I plug a 2 in, I get 7. 2 plus 5 is 7. If I plug a 7 into this, what do I get? 7 minus 5? 2. Okay, so F does something to 2. If I put a 2 into this, it makes it 7. F inverse undoes that. It takes it back to what it was. You understand? That's how inverse functions should work. One should be the opposite of the other one. They should undo each other. Whatever one guy does, the inverse function will undo. So notice what that means. All the inputs for this guy will be the outputs for that guy. All the outputs for that guy will be the inputs for this guy. You kind of with me a little bit? No? Okay. Does that by itself make sense? The fact that we know that addition and subtraction are opposites. Right? So these should definitely be the most basic kind of inverse functions there are. Right? So sure enough, when you plug something into here, you get an output. When you put that output into here, you get back to where you started. You get back to 2 where you started. Okay, all right. So that's the basic idea of inverse functions. What would that mean graphically? So if I had a function, let me see. So if I had a function like this, so this is negative 4 through negative 3. 0, negative 1, 1, 3, 4, 4. Here's my function here. Now notice something, I made this in a special way. One thing I did was I made it straight lines to make it easier to graph. But something else is every single, of course, to be a function, what's got to be true? Every input can have only one output. So this is obviously a function. It passes the vertical line test. To be something that has an inverse, if you think about this for a second, I have to be able to find where I came from. I have to be able to, if I know where I am, I have to know where it came from. Does that make sense? So 7 came from 2 in this case. That's what the inverse knows. So if I had a function that looked like this, like a parabola, and I said I have a 4 output, do you know exactly where that would have come from? What has a 4 output? If this is y equals x squared. Let me help you here. Nice parabola. What has a 4 output? 2 or? Yeah, it could be 2. It could be negative 2. Right? So, I would say this does not have an inverse function because I can't know where an output came from. There's 2 possible places an output could have come from. So this is a more stringent requirement. To be a function, every input can have only one output. Right? This is fine. That has only one output. That has only one output. But the idea of inverse is going backwards. So to be an inverse function, you also have to have every output can only come from one input. So this does not follow that. 4 comes from more than one input. So if it does that, it's called a 1-to-1 function. Which is a nice name if you think about it. 1-to-1. This 2 goes with this 7. Nothing else goes with 2 input. Nothing else goes with 7 output. They're 1-to-1. So here's the really cool thing. Visually, if to be a function you have to pass the vertical line test, every x has only one y. To be an inverse function you have to pass the horizontal line test. Every y has only one x. So to see if something's 1-to-1, to check if something is a 1-to-1 function, you just apply the horizontal line test. Kind of crazy. Hopefully that makes sense. It's really the exact same idea. If every x can have only one y, that's a vertical line test. If every y can have only one x, that's a horizontal. So would this pass the horizontal line test? No, it goes through more than once. That's the exact problem we were just talking about, right? Okay. Some of you guys are like, all right, what the hell? Is there a diagonal line test? Come on. No. Well, yeah, but we won't get into it. So how can I figure out, I want to know the graph of the inverse function. This is the function itself. How would you create the graph of the inverse function? What would an inverse function do with every point that this goes through? What did we just say earlier? It would just switch it. Doesn't change the sign or anything, it just switches it. All the inputs for the original function are now the outputs for the inverse. So what points does the inverse function go through? What points does it go through? Yeah, -3, -4.
-1, 0.
-1, 0.
3, 1.
3, 1. And then, can't go wrong with that one. Okay. So then to graph the inverse function, you graph -3, -4. -1, 0. 3, 1. 4, 4. Kind of neat. All right, good. I got a few of you guys like, I'll give you that, Jeff. That's a little neat. Where would the mirror be? Where would the mirror be that shows the symmetry between these two functions? Yeah. It'd be exactly there. Can anybody tell me what they think? Oh, a little cricket bow. What that equation of that line is?
0.
It goes through the point 4, 4. It goes through the point 0, 0. I'm trying to help you out. Y equals x. And think about it. If what I do is I switch the x and the y, visually it should kind of make sense that what happens is the graph just flips over the y equals x line. If I switch the x and y meaning, it should switch over the y equals x line. Because give me an example of an equation that wouldn't flip anywhere if it did its inverse, y equals x. So if I had y equals x, and I switch it, it's going to still be y equals x, right? Okay. So that, I'm going to give you a graph of a function much like that. I'm going to say just graph on top of it the inverse. Right? That's pretty damn easy to do, and hopefully it makes sense. The inverse will always switch the domain and range. You switch every point, and then regraph it. So that should lead to an algebraic. There's always got to be an algebraic way to do this kind of thing. I want an algebraic way to find the inverse. So if I give you a function like this, and I say find f inverse. And for some reason it's urgent that we do this. Find f inverse. Then how do you think I could do it? I mean, this is a very open question, but to get the graph of it, I switch the x and the y. And hopefully that makes sense. I think everybody was with me on board. That does make sense. It's exactly what should happen. So the really funny thing, maybe not laugh out loud funny, but the really funny thing about this is you do the exact same thing algebraically. What is f of x really? What was it before we talked about functions? What did that take the place of? Y. So algebraically, I do the same thing. I switch the x and the y. That just kicks ass, right? So if I switch the x and the y, I get x equals y cubed minus 2. Now think about this in another way. The inverse function should be the function that undoes all the operations. If I solve for y, am I not going to end up doing all the opposite operations? Think about it. How do I solve for y? What do I do first? How do I solve for y? Add 2. Hey, I'm adding 2. And what was my original function doing? Subtracting 2. See, I'm already doing opposite stuff. Does that make sense? I used to call this Memorex. It just keeps in memory. It just remembers all the opposite stuff. Because as you solve this equation, it's remembering all the opposite stuff. When I add 2, x plus 2. And then last step, how do we kill that cube? Cube root it. I love it. So take a cube root. Boop. That's the inverse. Look, the original function, what did it do first? Cubed the thing. What does this do last? Cube roots the thing. What did this do last? Subtracted 2. What does this do first? Adds, hey, it's the exact opposite function, right? That's really kind of nice. The algebraic way of finding an inverse is exactly the same as the graphical way of finding an inverse. You switch the x and y. Be happy when that kind of thing happens, right? Does not happen often in math. Just do the same thing. So if I were to graph those two functions, f of x and f inverse of x, how should they relate? How would they look? What would they do since they're inverses? Mirror image across the y equals x, just like that, right? So if I graph, here's what a cube looks like, roughly like that. And then the cube root would look something like, oh, what, Jeff? So we're going to do this careful. That. Well, I got my stuff in the wrong place, but they're reciprocal, they're inverses of each other, yeah?
How do you know this is the graph for this?
Oh, I just do. Just in case you're curious, that's what it would look like. Okay. So in the homework, you will get some that are just graph. You'll get some that are functions, and you have to find the inverse function. In the blue book, there's discussion in the section about composite functions. Not the blue book, sorry, the white book. The white book, and we don't talk about composite functions. Don't worry about those. Your homework starts with the inverse stuff. You with me? So if you're looking through the section, don't worry about the FOG, F-O-G function. Don't worry about that. That's composite functions. Don't worry about it. Unless you're curious about it, and then I'll tell you about it. So, say again?
14.1?
In the white book, yeah, 14. So, find the inverse for this real quick. Yeah. I don't know when I started doing this, but I always put a little dotted line because the next thing I do is not really algebraic, it's applying an idea. If you don't want to put the dotted line, that's cool. For me, I just have to do it. It's a little bit of my math OCD. So switch the X and Y. That's not an algebraic thing I just did. It's applying a concept, right? Now solve for Y. Yeah, add the 3. Then how do I kill? What's the next thing I have to kill? Yeah, good. I got to kill the 5th root, so I raise it to the 5th power. Right? Please, dear God, don't actually multiply that out. Good Lord. Hopefully, if you're trying to do that, stop. So here, that cancels, right? The power and the root cancel. That's the whole reason we did it. So we can free this stuff up. And then I just subtract 5. Divide by 2, right? So I take this, subtract the 5, divide by 2. That's my, G inverse. So this adds 3, but that subtracted 3. This cuts it in half, but that doubled it. You know, it's got all the opposite parts to it. Here's a funky function. So what does that function do to something? In what way? So if I put a 1/2 in there, what will the answer be? 2. So it takes whatever the input is and it flips it. So how do you undo a flip? All right, let's try. How do I find the inverse? What do I do?
X equals 1 over...
Switch the X and Y. Solve for Y. How do I solve for Y? It's being divided by Y. That's what sucks. The thing I want to solve for is on the bottom, so the first thing I do is free the poor dude up, multiply both sides by Y, to get him out of there. And one step away,
Divide by X.
divide by X. So the inverse of 1 over X is 1 over x. If you think about it, it only makes sense. If I flip something, how do I undo what I just did? Flip it again. Right? Flip 1/2, you get 2. How do I get it back to 1/2? Flip it again. So that's really kind of funky. This function is its own inverse. Which means the graph of it must already be symmetric to the y equals line, y equals x line. If you graph this bad boy, it actually ends up looking like this. So if I flipped it over this line, boop, it would just fall right back on top of itself again. That's kind of neat. Again, sort of neat. Maybe. Put a Beatrice. So this would be H inverse. Is that kind of nifty? Its own inverse. Okay. So graphically, you just switch the points, the x and the y. Algebraically, you just switch the x and the y, and you solve for y again. And that undoes all the operations. That kind of makes sense. It should end up with the opposite function, the inverse function somehow. What we're really working towards, the whole reason we do this, and I wish books always put this at the end. They should just put it with the normal function stuff. But the reason we do this now is because we're going to explore an entirely new function. And the minute you learn a new function, you have to learn its opposite. Because if I knew addition but didn't know subtraction, I could never solve an equation that has addition in it, right? To solve an equation, I have to do the opposite. So we're going to learn exponential functions, and then we're going to learn their inverses, which are called logarithmic functions. And that just sounds remarkably heinous, but it is not remarkably heinous, right? You know, like, yeah, you say that. You know this stuff. Let me see. Just a little bit more here. So, if you think about it, we've put variables on the bottom of stuff. We've put variables with powers on them, and then added them to other powers. We put variables under square roots and radicals and all kinds. We put that damn variable almost everywhere we could think of in an equation. There's one place we definitely have not put it yet, right? And so you guys are thinking, that's the only way you put it. Whenever I say something, somebody's got to be thinking that. The one place we haven't put it yet is itself as the power. And this is not just playing around with stuff. I mean, this is very useful. This would be a good function to model if something doubles every so forth. So if you have a little petri dish full of bacteria, and they double every 2 minutes, this would model how many bacteria there are. If you start with 1, it would tell you how many there are after so much. You with me? Sort of. Okay. So, whenever we have a brand new function, the very first thing we do is we graph it. So I know you're not going to do this, but if you did take pre-calculus, that's basically what you do through the whole semesters. You learn a new function, you graph it. You learn its inverse, you solve equations. You learn a new function, you graph it. You learn its inverse, you solve equations. I mean, that's what pre-calculus does. It gets you ready for calculus, which is real-world stuff. So here, the very first thing I want to do is graph this bad boy. So I want to make a table, because I don't know what the hell this thing does. So when you have a brand new function, you don't know what it does, you make a table of values to get a feel for what this thing's going to look like. Whenever you have a brand new function, you don't know what it does, you put in a variety of numbers. You put in some negatives, you put 0 in for sure to see if 0 freaks it out or not. You put some positives. So I'd put in, pretty much my standard thing to start with is those 5 numbers there. So take a minute and fill that table out. Be really careful. What does a negative power mean? What does the negative power
1
mean?
over something.
Flip it. Yep. All right, let's see. So what is 2 to the negative 2?
1 over
1/4. I like it. 2 to the negative 1.
4. 1 over
1/2. 2 to the 0. 1. Not 0. 2 to the first 2. 2 squared. 4. I like it. So if we plot this thing, and just imagine this going forever back. Let's not do it. Well, if I put in there negative 10, that would be 1 over 2 to the 10th power. Are you with me? That's not equal to 0, is it? That's just some very small number. If I put in there negative 18 trillion, that would be 1 over 2 to the 18 trillion. Is that 0? No, it's just very small, right? So do I ever get to 0? The biggest negative number you can think of, if I raise 2 to it, it's not going to be 0. It's going to be 1 over